All right, so we are happy to see you today at our Bridges-2 webinar. Welcome. Um, so first of all, welcome to the Pittsburgh Supercomputing Center. We are now in our 40th year, and we do great things. And specifically, welcome to the Bridges-2 project. Which is a NSF-funded project to provide resources and services to the national uh, user community. And my name is Sergio. I'm the PI, so I would like to welcome you on behalf of our leadership team here. And Paula, for example, is right here. She just helped to welcome you. And so what we do here is we have this Bridges to webinar series. Did I just stop sharing?
I'm not seeing your screen. Yes, Sergio, so you'll need to re-enable this sharing.
Okay. Sorry for the snafu here. Um, Well, anyway, I'll just, there seems to be a problem here. So I'm just saying the Bridges-2 webinars are a forum for the Bridges-2 community to learn and share ideas and achievements. Um, if you have any topics that you think should be covered that you yourself are working on, or if you want to suggest speakers that would be of interest, including yourself, please just send email to me, sergio@psc.edu. So then I'd just like to introduce today's presenter, Daniel Justice. He's a researcher in the AI division at the Software Engineering Institute at Carnegie Mellon University. His work focuses on the intersection of quantum computing, machine learning, and large-scale systems, with an emphasis on evaluating how emerging quantum methods perform in practical settings. In addition to his research, he teaches a graduate course on quantum computing, cryptography, and machine learning at Carnegie Mellon. And just in terms of logistics, we do abide by the Access Code of Conduct. So if anybody, again, sergio@psc.edu, if there's anything off that you noticed today. All of us except the speaker will be muted during the presentation. So we would invite you to type your questions into the Zoom chat, and we will try to resolve some of them as we go. But then after the presentation, Dan will answer the questions that are hard and are left for him. And as you know, after some few days, then the recording of this webinar as well as Dan's slides will be up on our webinar series webpage. And so with that, I already stopped sharing, unfortunately. So are there any questions for me? If not, then Dan, please take it away.
Thanks, Sergio. And thank you so much for having me here. Uh, Sergio and his team have supported my research since I've started here at SEI. And what we've done so far and continue to do wouldn't be possible without PSC, Bridges, and the compute. And I'll show you some of that pipeline there because I have certainly learned a lot of lessons over the last couple of years as far as how to be a better steward of what Sergio and his team have given me the opportunity to use.
Thank you very much, Dan.
All right, let's set this up and there we go. Oh. Okay, so as Sergio mentioned, this is topic is going to center on quantum machine learning, but really we're going to be focusing on what HPC enables and what quantum hardware actually delivers, right? There's an interplay that's necessary here, and we're going to talk about that a little bit and how we navigate this. Just regular document marking so that, this is distro A. You can pass it along as much as you like. I like to start off with maybe why you might want to listen to me on these topics. I have several affiliations. My main affiliation is with the Software Engineering Institute and the AI division, where I act as a researcher and developer on quantum and AI. I also am part of PQI, the Pittsburgh Quantum Institute. They did just have their conference for 2026 this last week, where uh, I saw everyone here at PSC, Sergio and Riaz and Paolo. And if you missed it, I really suggest it. It's an absolutely amazing conference. You can learn a lot and you can really plug into the experts in this area. Um, and there'll be a 2027 one. I also teach at Carnegie Mellon University, and I'm also a courtesy researcher here at Pittsburgh Supercomputing Center, which really unlocks a lot of the potential here. And if you hit those QR codes, they should take you to each individual affiliation. Uh, Talking specifically about my quantum computing classes, is everything to, the one on the left should be all of those classes, and I have several co-instructors. These are classes that tend to be more hands-on than theory. I really, really mean it when I say I'm teaching you how to program quantum computers. And I teach you the algorithms as they go. I really, really like the attitude of I will teach you. I call it quantum mechanics on demand. I generally assume that most people understand computer science coming in, and we will teach you the quantum mechanics and the quantum algorithms as you need in order to program. Um, Anyways, it's been fabulous fun to teach these courses with all of my colleagues. It's been marvelous. Um, Okay, so let's actually jump into what we're here for, right? The QML approach. What is quantum machine learning? All right. So the first thing is, what does quantum machine learning promise? The promise is also potentially that what we could call hype, but a lot of what I see people are hoping quantum machine learning will do is kind of attack some of the weaknesses that are happening in modern day machine learning. And the biggest issue that we have is that the scaling issue. Um, Modern machine learning, especially LLMs, which are really in vogue right now, is that they hit these bandwidths where you can only get so much better by adding compute. And so there's this line that happens where, to get any better, you have to do a linear or sometimes exponential amount of increase in compute power, in data size, in parameter matching, and you're just grinding through data as much as possible, and you're grinding through power as much as possible. And quantum machine learning is the hope that somewhere in there we can either find fewer training cycles, less power per cycle or epoch, more robustness. Like we're looking for some sort of advantage, and there's likelihood that there might be this. The math behind quantum is eerily similar between that and what a lot of machine learning looks like. But we do have to be careful with this. I have lots of opinions that we won't quite get into as to how to get the best out of quantum machine learning in today's world, but we're going to leave that on the table for now. Either way, many people are looking to quantum machine learning as a solution to honestly, our budgets, energy budgets, cost budgets, every kind of budget when it comes to machine learning. But the thing about quantum machine learning is it's a hybrid workflow. Okay, it's not all quantum. There's this part where you will execute your quantum circuit generally on a quantum computer. And then the optimization or the learning tends to happen classically. And then it goes back into this loop, right? So that's going to be the hybrid loop that you have there. It's also very tricky. Quantum circuits tend to produce they don't tend, they do produce probabilistic, non-deterministic outputs. And if you're not, a lot of times you'll have to run that multiple times in order to get what you want. There is one-shot inferencing and learning, but that's, you know, we don't always use that. It's not always the appropriate for the application. Um, and again, the classical optimization is going to drive uh, the parameter updates, right? So compute for quantum machine learning, a lot of the heavy lifting tends to be done on the classical hardware, not necessarily the quantum hardware. And we really do want to keep that as much as possible, and we'll show you why soon. And so one of the reasons also why quantum machine learning is a hybrid solution is because quantum computers by nature are hybrid. In fact, actually, when we talk about hybrid, depending on where you put hybrid in your name, kind of depends exactly how much of a hybrid approach you might have. But every quantum computer we have out there is hybrid by nature. It is all going to be a quantum computer is generally a classical compute unit, a CPU that controls uh, one or more QPUs, so quantum processing units, and that gets all wrapped up, and that's your quantum computer. And one of the reasons that we know that has to work like this is because you yourself are a classical individual. You can't interact with the quantum state. And so there has to be this classical to quantum interface and then back from the quantum to classical interface. And generally that quantum to classical interface is measurement. Um, and and so this is going to be your quantum computer. And obviously it gets way more complicated than this. But the way that this is going to work eventually, like the idea that many have as to how this is going to work in our ecosystem, is that quantum computers are going to be an option on high performance compute clusters. And so you'll be able to interact with HPC, and you have many different types of resources, right? You have your CPU, you have your GPU, you have your storage, but one of the possible units is going to be your quantum computer. And so you can hit that. And you're not just going to hit that in isolation, just like we showed earlier, is you're going to need to allow for these loops and these interactions between your CPU, GPU, storage, and quantum computer. And unless you're doing fundamental research, you're probably going to want to hit that quantum computer only when you need to, because I will show you later on, it's expensive, right? It's going to be the most expensive resource here, unless, of course, they come up with a new type of advanced compute unit, maybe some neuromorphic compute of types that is even more expensive. But it's hard to beat the price of a modern day quantum computer. And by beat, I mean be more expensive. And so this is going to be our general setup that we maybe are hoping to see as we go into the future. And again, going back to exactly where HPC fits in a normal cycle um, for quantum machine learning is that you end up being in these cycles where you start with an ansatz. So the ansatz is the almost you can think of it as the kernel to a quantum machine learning circuit. That ansatz gets transformed into a quantum circuit. And normally you would run that on a quantum computer. That would be the natural thing to do, right? You would hit this QPU up there, and then you would process that, you would measure it, and then it goes onto your classical computer where you have your post-processing, your classical optimizer, especially if you're doing the training instead of just the inferencing, and you crunch a whole bunch of numbers. That right there needs to be done on a large compute cluster, especially if your circuit is large, especially if you're using lots of qubits. And this is where you can expect to see that HPC jump in. Um, but you'll notice I also have Bridges-2 over here on the execute side of where the QPU could be. And so the QPU is really an option. You only want to hit that if it makes sense because it's hard to hit, it's expensive, and it's slow at the moment. And we'll get into that in a second also. And so most of the time that I'm doing this, actually, I'm just running simulators on Bridges. And you do need, if you want to run a simulator, honestly, if you want to, depending on the type of simulator that you want to run, but a lot of the ones that I run tend to be state vector simulators. Anything that starts to get beyond like 26, 27 qubits, you're going to need you're just going to need Bridges-2. My poor laptop doesn't like that many qubits. And so either way, um, what you'll notice is most of the time we're running on on HPCs of some sort. And it's what enables us to train. It enables us to scale to what we need to, and then we hit the QPUs when we're sure that it's the right time. Right. So we do this all the time, and I'm going to take a moment to kind of look at one that we've done somewhat recently, which is we took a look at QCNNs. These are quantum convolutional neural networks. This got very popular for a couple of years there, and this one specifically has been looked at a lot. It's the famous Kong et al. QCNN architecture. And it's been implemented pretty much most places. You could find it on Qiskit. You can find it in random packages. I believe you can find it on Penny Lane. So it's there. It's generally not implemented um, true to the actual paper, and so that might take your own efforts to make that translation. We certainly did to make sure that it was absolutely right. And this is uh, I will say we are definitely at the stage within quantum where you oftentimes have to build your own models because, well, there's not a Hugging Face that exists that has quantum models in it. We're still at that research level. Okay, so either way, a QCNN, you can see up here that we have at this part A, what looks like a way to think of convolutions classically, and then we have a manner in which this is a quantum circuit in B, and we have input go in, and there's a manner of doing convolutions and also pulling layers that they have. And so the convolutions tend to be an entanglement between two qubits, and the pooling is an entanglement between two qubits and a measurement on one of them that will reduce your size down into a smaller convolution on the next step. And this is our implementation of that. So you can again see that architecture up top, and then on the bottom, you can see that we have highlighted in blue is the convolutions, and orange is the pooling layers, and then at the end they have what they call a fully connected layer, which is, you can, if you look over there, you'll see there are two C knots over there with some angle rotations. And so that's going to be your fully connected. Over here on the left, we have a data encoding. We chose a simple data encoding. Is simply angle embedding. And we did that for multiple reasons, but one of them is to reduce the circuit depth. Reducing the circuit depth helps us out later on as we put this onto a real quantum computer. Again, going back to what the experimental architecture looks like is it's a cyclical part where you have data going in this case, we have a 3 from MNIST, gets compiled down, or not, that was called compiled down. Classically, it gets reduced down to a 6x1 vector. Each one of those features gets encoded into its single qubit using angle encoding, which we saw previously. Then we perform that QCNN um, uh, uh, circuit, which is the convolutions, the pooling, and then the fully connected. And then finally, we measure out. From there, we can compute the digital class classically, because once we measure it out, back in classical domain. And we have these two loops, right? So we have to repeat this for each shot, this quantum part, and we have to run multiple shots in this algorithm in order to compute that digital class. Anywhere between like about 500 to 1,000 shots tends to be a good area to kind of get something that's statistically meaningful. And then outside of that, this has to be done for every image. And because the encoding part of the circuit is unique for every single image, for every 16 by 1 vector, that comes from every image, you end up needing to create a new circuit for every image that you are going to run this for. Um, and so this can get, computationally quite expensive, right? There's a lot of classical compute that goes into recreating each one of these circuits and then running it. And again, it's a lot of loops that go on here, and they add up. Um, and they add up a lot, right? So then we take this and we move this from real to simulation. What was our end goal? And you can see for a single inference of an image over here on the right, when we run the penny lane on a large computer, because we're hitting 32 qubits, right? So we're using quite a decent amount of resources. Our inference time is like 0.147 seconds. It's less than a second. It's still not fast. A Raspberry Pi can do this task quite a lot quicker, but we're using up a huge number of resources in order to represent and simulate a quantum state in order to do this. So it makes sense that it's taking this time, but it is quick. When we hit real quantum computers, we saw that our average inference time went way down. We used Amazon Braquettes, and we used the 4 quantum computers that were at that time available that could run the circuit. Um, and you can see that only one of them runs in less than a second. Most of them run in slightly more than a second, and some of them take minutes, if not hours, to run. That almost like when you get up beyond a second, uh, even fractions of a second, most of that actually comes down to queue time. And so we're stuck in queues, and it's very hard to differentiate how long it would take if it weren't. But generally, you would be a little bit closer to half a second, I believe. The cost per inference can change drastically, everywhere from 75 cents for inferencing a single image, to $40 for a single image. And so if you're running this, you can see we ran 40 inferences at 512 shots each, and IonQ is going to cost you about $2,000. If you run it at the much more preferred 1024 shots, you're hitting $4,000 for 50 images, just about. And yeah, and also if you look at like it's also taking you hours to do this. Um, so right now, quantum computers are extremely expensive. Um, They also have other issues, such as your simulation is going to be the best because you can simulate without noise. And so you can get the best results from that, whereas every quantum computer is going to have more noise. It's hard to, it takes a lot of preparation to put it onto a real quantum computer because each one is slightly different. You've got varying quality of qubits, you've got varying architectures. And so it takes a lot of hands-on expertise right now and a lot of elbow grease to target different quantum computers. You can do certain things to speed it up and let it kind of just go, but a lot of times you're going to hit an accuracy issue if you're not doing something intelligent there. And so yeah, the sim to real challenge and why this is degrading is again because you have a circuit. If you look in the top left, we have this primitive circuit that you want to run, and you run it on an ideal device that you can simulate on bridges at because we can simulate large-ish devices on bridges. And we get what we want, right? Like the function is acting how we want it to act. But then when I move it onto a real quantum computer, you end up having it's a noisy device, and you tend to have this movement. And we saw this, right? We saw other noise, but you also see the movement away from the function. And so there are methods to fix this. And one of them is error mitigation. So you can come down here and you then need to use bridges again to input noise, which costs even more, and create new error mitigated circuits that you can actually pull from. And depending on how you do it, sometimes you got to pull from different ones based off of the scenario, and you can then recorrect your function, your expected outputs back over to this center line is what this is attempting to show. Um, and of course, these errors drift a lot more with the higher, the larger and more complex your circuit is, especially the depth. Um, and so that this ends up being a little bit of I wouldn't say necessarily a cat and mouse game, but it ends up being this optimization game as to how much you can actually put into, you know, training for the noise, mitigating for this, and also hitting uh, the number of qubits that you're hoping to, and maintain the accuracy and power of your model. And so there are a lot of hyperparameters to mess around with here that you can go down a rabbit hole. Um, Right. And of course, as you actually go and hit these real quantum computers, you're just hit with a bunch of operational constraints. The biggest one that you end up finding, for me at least, that I don't like is the queue. I don't like being stuck in a queue. It's very variable. It can take an experiment that you expect to take half a day, and it can run for 3 days. Um, and and so that's rough. Also, the latency, the amount of iterations that you can get through is extremely reduced, not only by the time it takes to do this, the variable time it takes to execute on modern day quantum computers, but also the price. You only get so many runs with the price tags that you want, that you see, especially on the quantum computers that are better. They get really expensive really quickly. And so you had better make sure that those runs are well worth it. And yeah, that is where this experimental progression that we've really started to become pretty adamant about begins, right? And it's pretty obvious once it's said, but we didn't always adhere to this process, and it has always hurt us when we haven't. And it's that we start off with small circuits on laptops, right? You pick a topic, you pick an algorithm, you pick an application, and you figure out what you're doing. It should be able to run with few qubits, small numbers of features. These are toy problems. We're talking 8, maybe 16 qubits max, but really closer down to sub 10 qubits. You debug your circuit, you debug your process, and you get it going. Everything should be changing hour by hour, day by day at the slowest. Once you're pretty sure you have something, you want to then move it on to larger compute. And larger compute, when you're dealing with quantum computers, scales really, really fast. You may be able to do 16 um, qubits on your laptop, but by the time that you're at like 25 to 30, you're going to want it to be on something similar to Bridges. if not Bridges-2. And then by the time that you get to, I don't know, 45 to 50 qubits, you are talking about having two bridges twos, or just doing something different or changing the way that you're simulating. Because after you hit about 50 qubits, it just becomes really too large, even for a lot of supercomputers using state vector simulators. Um, and so you're now in an area of you have to change up your simulation, you have to change up your tactics. Um, Once you hit that, once you've run that on bridges and you're pretty sure that you have what you want and you're going where you want to go, then you can finally hit your QPU. And we really only do this for final testing. We want to see what the noise effects, we want to see what a real device behavior looks like. And that first one up there, the real device behavior that I have listed, is really important because sometimes many a times, we just stop at Bridges-2, right? Because we don't need the real device behavior to make the point we're making a lot of times for our research. There are times where we still need to see how much truth is in the pudding per se. And so we will hit it, but we try to stay away because we're happy here on laptops and HPCs. Um, and so, yeah, just like you see right down here, we scale understanding first, and then we move up in the hardware that we hit. Um, and that is my main guidance for you is like use HPC, use bridges when you're training your QML models, when you have a lot of data going through, when you're crunching your compute, when you're training your models. It just all the time we are hitting it. We use it to explore our circuit architectures and our parameters. We put it through its paces and see if we're missing anything. Um, and we also set it up to orchestrate our hybrid optimization loops. It's taken us a long time to find out a lot of what is now standardized within the community as to how you should be looping these systems and where we expect these quantum circuits to look. Um, I just had a conversation with some new researchers I met at PQI the other day, and they want to be on bridges right now, and I'm like, you will be soon, but we aren't even sure where we want our hybridization loops to be. We're still that early on. We know the algorithm, we know um, the application that we want, but we haven't even built the first small 4 to 8 qubit circuit and seen where it actually fits, where that hybridization loop fits within the application. And so then once they do that, then we will move them on to HPC. And then if that's really successful and they think they have figured out something there, after one or two more papers of showing the validity of it at scale, we then will move them to QPUs if it still makes sense. And that's where it's going to show that, hey, this works. This works on bridges. This works on laptops. This works on bridges. We expect it to work on hardware. We need to make it work. And then there will also be for showing techniques on how to make it work on real hardware because that's its own talent. Um, and so hopefully we'll get to that point, and soon that group will be on HPC along with my other students. All right, and that pretty much brings us to the end. Um, the key takeaways of this, of course, are classical computation dominates QML workflows. That's not necessarily a modern day thing. That is how QML is currently set up. The quantum part solves a very small part of a hybrid solution, and a lot of that is all going to be classical. Um, Quantum hardware is tough to work with. It takes specialized people and knowledge to work with, and if you want to stay away from it because a lot of what you can do on the quantum hardware can be proven with classical hardware. And then it's that integration problem that you're going to spend a lot of time. So only do it if that's what you want to focus on, or it's really needed to prove your point. Um, Simulation and hardware results can diverge significantly. We have seen accuracies without error mitigation techniques. We have seen accuracies drop by over 20% on models just because we moved it to hardware. There's many reasons for this. Oftentimes it's because we were not careful when we were building stuff because we have so many resources that we didn't think that we needed to be careful with the size of our circuits because we got a little spoiled on the classical side. And so now our circuit depth got too long. Um, Anyways, there's other reasons why it diverges, but that was an operational one that we found out. And HPC is absolutely essential. It's right in the middle of a pipeline where we do this from small to large to on real hardware. Um, so yeah, I mean, quantum machine learning is a systems problem. It's not just a quantum problem, and we need these large systems to solve them. And that would be it. Thank you.
Thank you very much, Dan. Thank you. So we have started to get some questions in the Slack, in the channel, in the
Hmm.
chat channel. I don't know if you can see them. We have
Yeah. So, um, I got a question from
Hadi.
Hadi Sahin, and it says slide 13. Do you usually build quantum circuits from scratch in QML or rely on predefined templates? That is a great question. Thank you for asking that. Uh, we Nowadays, we generally build them from scratch. And the reason is actually this specific this specific image right here. We and one before it actually, but we oftentimes tried to bring in implementations from different frameworks, and we found that oftentimes they are inspired by papers and they're not true recreations of them. And so we thought we knew what we were benchmarking or modeling or training, and we weren't. We were training something different and it was behaving differently than anticipated. And so we have all but stopped importing stuff from today's libraries. Um, we're not at the same stage as we are classically, where there are publicly hosted models and that they're under review and updates and iterations. Most of these models are done by a developer that puts it up on GitHub, and you pull it down, and then you also have to train it yourself. By the way, almost no, it's almost impossible to find trained weights on a quantum model. They exist, but they're very rare. And they're again generally locked away in somebody's GitHub repo. Uh, can you share that? Pre Prathush asked if you can share the PowerPoint. Yes, I think Sergio said he will
Yeah,
share this
yeah.
PowerPoint. Um, then Yao Liang asked, in QCNN architecture, how do you compute the activation functions like ReLU between layers as ReLU is nonlinear? Oh man, you ask the hard questions. Okay, hold a second. Let me load that one up for a second. So, there's a couple of ways of doing it. Um, this is one of the reasons why it's important at this level of doing quantum machine learning. Like, so it is to use large compute, is I can actually treat this circuit at its size, especially at this size. This size is not too bad, 16 qubits, but a little bit larger, and then it definitely has to be on bridges. Um, I can treat this circuit as completely classical. Because I can simulate the whole thing, and then it is actually deterministic then. And then I can run back propagation. through this and I can change the weights, which the weights in this end are rotations. And so you will change those, and then it just kind of almost works like a classical. Uh, it acts a lot more classically than you might anticipate in that functionality. When you can't use a classical computer to simulate it, you end up doing, I'm trying to remember what it's called. It's called gradient something, but you end up going and you rotate for every single parameter you have, you will run the quantum circuit and you will run it with each parameter shifted down or shifted up in rotational space, and then see what your loss is for each one and move it according to what value is best. It's extremely, extremely expensive to train a quantum model on a quantum computer, or at least a QCNN on a quantum computer. Um, we are talking months of compute time on a quantum computer. I believe that JP Morgan Chase and IBM did something similar to this in 2023. I think there's a paper out there. And it's prohibitively expensive. It's not it's not something that I am in the situation. If that's not enough, reach out to me later and we can go more in depth to this and we can bring up some textbooks. Um, Slides and recording will be posted. Is there a fundamental limit that oh, sorry. Again, thank you for that, Yao Liang. I'm now on to Muhammad Ali. Is there a fundamental limit that the performance of QPUs, QCPUs, so quantum computer processing units, could cap out after? In other words, when we do superposition of states, the dimension of the Hilbert space exponentially increase. Can we explore every portion of that space, or is there a fundamental limit? Oh, what a good question. Thank you for that. So you can explore every part of that space. But at this point, that's no different than running a classical simulation of it and hitting every point in it. You're limited by time there, and and so you can do it. And depending on how large your space is, how many qubits you have, and how much entanglement you have, and everything, like you very quickly after like 100 qubits, in order to hit every one of those points, you're going to hit the heat depth of the universe. So you can do that. It's just not how I suggest using a quantum computer. The way that you use a quantum computer is you raise the input, you raise the dimensionality up into up into a higher state space, like exponentially higher state space. You then contort the data in such a way that when you like projectively measure and you push it down into one dimension, because that's what a bit string is, that bit string gives you um, a clue as to what that structure was up there. And that structure itself is the answer generally. Like that structure you built up in higher dimensionality, that has in it the answer. It either is the answer or has in it the answer. Um, and your projective measurement gives you hints on that, right? And so what this does is this prevents you from having to visit exhaustively every point in in that exponential state space. You're just getting the projection out and figuring something out from that. Um, Great question, Mohammed. I hope that made sense. I love that question. Okay, Saham Paul is getting many questions, or sorry, many hearts. And it says, not model weights, but Penny Lane shares data sets that you might find useful for QML. Yes, yes, they do. And they also have an amazing paper out there. Maybe it's 2 years old now, talking about what data sets to use and for benchmarking and everything. It's excellent. Yes, I also will heart that. That is they. I use Penny Lane extensively, and they are very pivotal to this type of research. Um, um, let's see, Jeffrey Dale. Yeah, at Yao Ling. QML has alternate flavors of nonlinearities. Yes, data re-uploading, Rust, and other methods can achieve this, but there isn't a one-to-one correspondence with classical nonlinearities, to the best of my knowledge. Yeah, that's a yes. Okay, yes. Jeffrey, that's absolutely true. And I'm using QCNNs not because I even think actually that this has an advantage over classical. Um, CNNs, but because it is a good example of what you can expect in QML today. And many people already have experience with CNNs. And so this is to kind of bridge the knowledge gap in case you're not familiar with some of the more specialized QML algorithms. Parameter shift rule. Yes, so Ham, thank you. It is the parameter shift rule that I was trying to describe. Thank you. Um, that the parameter shift rule is how you will train um, a quantum model on a real quantum computer. It's one of the options. It's very expensive. I'm currently, let's see, ban train. It's either ban or bon tran. Uh, I am currently attempting to train my models using GPU acceleration, specifically utilizing Lightning GPU of Penny Lane. Excellent. On the Bridges-2 system. However, despite loading the CUDA module and attempting to initialize the GPU, the server reports that no GPU devices are available. Could you please clarify if this issue stems from an incorrect library configuration of my environment, or if there are additional administrative procedures or resource allocations I need to request to access the GPU computational nodes? I will say you need to make sure that you have allocated both your GPU and CPUs. But
So Dan,
this,
I did, Paula and I already kind of suggested that
okay.
maybe, first of all, Dan might want to look at the user guide and then submit the ticket and we'll work on it. I don't know if it's necessarily something you can help with, but if you
Yeah,
have
no,
advice, sure, by all means.
I will say Sergio is absolutely right. Aside from what I had said, I go to Sergio and team for these exact problems.
Mhm.
So
Yeah.
they can help you out, and this is a
Yeah.
great place to ask that.
Yeah, and
Um,
again, the first stop is again, in terms of looking at how to like make sure you have all the resources you need in terms of the Q sub, like how to submit the job. You can we tried to explain that in the user guide, but then you know, to investigate your specific problem, just describe it in a message to help at bsc.edu.
yeah. Um, let's see. Yes. Okay, moving to Zheng. Um, when training models using a QPU, are we effectively optimizing a parameterized quantum circuit rather than a classical model as a traditional HPC flows? Given that the increasing circuit depth to improve expressivity also introduces more noise and errors on current hardware, what is the practical advantage of this approach today? In other words, how should we think about scalability and real-world usefulness of quantum models training under current noise constraints? Okay, let's great. I'm glad you asked that in three-part questions, and we'll attack all three of those. So the first one, when training models using a QPU, are we effectively optimizing a parameterized quantum circuit rather than a classical model as in traditional HPC workflows? Yes. Most QML at the moment is a parameterized quantum circuit. Um, and I personally don't see much difference between that, like an overly large difference between that and training a classical model in a sense. But yes, it does have slightly different workflows. It does have slightly different nuances. So that is exactly what's happening. Given the increased circuit depth to improve expressivity also introduces more noise and errors on current hardware. What is the practical advantage of this approach? Given the increased circuit depth to improve expressivity also introduces more. Well, yeah, so practical like what is the practical advantage of this approach today? I would push back and say practical advantage for what? Because it depends on what you care about. I can say that it is a balance. Let's say let's say you're doing research into figuring out exactly how good certain quantum computers are for compared to like previous quantum computers or something like this for QML, you're going to want to increase circuit depth more and more and more in your models until you start to see a degradation in your accuracy because of the noise that you're talking about, because you're trying to gauge, okay, how much information can I actually express in this circuit on this specific quantum computer. And so you would mess around with that. Overall, you really want, like, if you have a perfect quantum computer, you want a fairly long circuit depth, um, because, like you said, it increases expressivity. I will warn you though, like we can get into the dangers of too long of circuits, and one of the biggest ones is assuming an ideal quantum computer. Your gates on a quantum computer are way slower, like 1,000, 10,000 times slower than a classical gate. And so you need to make sure that each gate is doing its fair share of the work. And if you go too long with any quantum circuit, you're just you just got to be careful because the actual execution is fairly slow, and so you got to make sure that you're using a good algorithm that gives you good advantage. Um, in other words, how should we think about scalability and real-world usefulness of quantum model training under current noise constraints? Yeah. Um, I think that I personally like to kind of, if you want to do dichotic thinking, I like to, which you shouldn't, but I do. I partake. I like to split it into kind of two worlds where one world is trying to find really good algorithms and prove that they exist not only theoretically but experimentally. And so you should think about like training and scaling to quantum models right now, uh, classically, especially to trying to figure out any kind of proof that there's an advantage, especially as we scale to a larger number of qubits. And then the other side of it is, okay, we're just going to assume that one day somebody over here is going to figure out one of these models that has crazy advantage, and we're going to prepare for that, and we're going to show that once that exists, we can map it from simulation to a real quantum computer in a reasonable amount of time, because we gotta prepare for that. And so it's kind of like the difference between like the pitcher and the catcher in baseball, you know. I hope that makes sense. Um and so I think that's how you should frame why, like, where people are trying to figure out the scalability. One's trying to prove that scalability uh is trying to find an algorithm that shows promise and proves that it shows promise as you scale. And the other is like, okay, when we do have to scale and we have to put it on here, how do we do that? Um,
Well, thank you. I think we're at
uh,
time, but we have
oh,
maybe the question from Lu Wei, if you wanted to address that.
sure. Lu Wei, Schultz's 2024 benchmarking papers showed that the best performing quantum models are the ones most similar to classical ones, like projected quantum kernel resembling a Gaussian kernel. Do you think this means we just haven't found the right inductive bias for quantum models yet, or is there something more fundamental going on? Yes, there's a lot to be said about that paper. I am not sure that there can be anything decisively said about the question that you're specifically asking. I do have a feeling that fundamentally we need to think about QML slightly differently and change our approach to the algorithms. I think that there are other algorithms I would have liked to see them benchmark that have come out recently. We, I can talk about that in more detail if you reach out to me. But they had an amazing, their paper is amazing, but there's definitely more work to be done on that front.
Then, as a parting gift to folks, would you like to maybe put your email in
Oh,
the chat? And then, if you're willing to entertain questions after we say goodbye.
yep. There is my SEI email. Please feel free to reach out. I love to talk about this topic. So please.
Yeah, because I think people were like very stimulated by what you said. So you may very well get follow-on messages.
Awesome. Thank you so much.
Thank you very much, Dan. Thank you very much, everybody, and have a great weekend.
Thank you. Thank you,
And like
Sergio.
I
Have a good
said,
one.
we do hope to see, we do hope to be able to post the recording and the slides next week. So you will get an email when that's done. Thank you very much.
Thank you.